So welcome to lecture 7. This is the main point of this lecture is the fundamental theorem of arithmetic. To make sense of that, we need to talk about what is a prime and what's not for a little bit, and then we'll get to the fundamental theorem towards the end of this lecture. So to start with, what is a prime? A integer, positive integer I could say, is called prime if the only positive divisors of p are 1 and p. We also assume that the integer is larger than 1. All right, so the number 1 itself is not a prime. Okay, so the first prime is 2, then there's 3, and so forth. Right. Now, in some sense, this definition is a little bit ad hoc, because if you just think about divisors, right? Think about like a divisor of 7. What is the divisor of 7? Well, you've got plus or minus 1, and you've got plus or minus 7, right? So there's not a unique, it's not like there's just two possible ways to divide 7, right? You've got plus or minus 1 or plus or minus 7 as possible divisors of 7. But for the purposes of, for the purpose of just keeping things, easier to discuss, essentially, it's a long-standing practice to just look at positive divisors. And so we'll continue that practice, all right? But in the larger scheme of abstract algebra, I would mention that that's kind of a special quirk of the study of integers. Okay, anyway, so prime is a positive integer larger than 1 that the only divisors of it are itself and 1. Okay? So notice that if n divides p, that means that p is a multiple of n. Right, and so of course the absolute value of p is larger than the absolute value of n, but since both n and p are positive, we have 0 is less than n is less than or equal to p. So to check if p is prime, we need only check if 2, 3, 4, all the way out to p minus 1 are divisors of p. Okay, but maybe you already know that we can do better than that. So we'll see that shortly here. First of all, definition. An integer n is called composite if there exist a and b between 1 and n, all right, so such that n is equal to a times b. So you don't want to let a or b be 1, because then you get the silly thing, n is equal to 1 times n. Ooh, that doesn't count, right? So we want a and b to be not 1 and not n, so they're, it's a genuine, I would say, a genuine reduction of n into a product of two integers which are smaller. Okay, and so here's the proposition: n is composite, then there exists a such that a divides n, and a has a value which is between 1 and the square root of n, possibly included. The square root of n is included, the 1's not included because it's not interesting. Okay, so how do you prove that? Well, I guess I probably should move this up a bit here. Sorry if I've been off the edge of the universe, so to speak. Hopefully not. So here we go. Suppose n is equal to a times b for some a and b between 1 and n, and then towards a contradiction, excuse me, suppose both of them have value larger than square root of n. Well, then you get n as ab is greater than the square root of n times the square root of n, which is n. N is greater than n. We can't do that. So therefore, by proof by contradiction, what we assumed must be wrong, right? So not both a and b can be greater than the square root of n. It must be that at least one of them is less than or equal to the square root of n. And that's the proposition. So this means to check whether or not a given integer is prime, which we say is checking the primality of n, we just need to check divisors up to the square root of n, which of course we can approximate with our calculator if we want, right? So, excuse me, n equals to the 42. Well, the square root of 42 is about 6.48. So in principle, I only need to check 2, 3, 4, 5, and 6 to see if this is actually prime. Of course, we know it's not prime, right? And as you can see, by the time you get to 2, you already figured out it's not prime. Okay, so actually point of order here, even numbers are not prime unless what? Unless we're talking about 2. So in our search for primes, we probably should just think about odd numbers. Something I routinely neglect in the next 2 lectures, all right? Like, there's always this refinement that could be made in many of our arguments. Just look at the odd ones, 2 is a special case. N equals 35, well, at least that's an odd example. So here the square root of 35 is about 5.91. So if we check 2, 3, 4, and 5, if none of those divided 35, we would know 35 was prime. And 2 doesn't, 3 doesn't, 4 doesn't, but 5, well, 35 is 5 times 7, so, oh, there you go. It's composite. Okay, so we'll come back to the subject, to the problem of testing the primality of integers later in lecture 7. But for now, I'm going to go on. So this is proposition 2. Let get it into position here. Let P be a prime. Suppose A and B are integers. Then either, now here I'm not assuming that A and B are positive, okay? But we are looking at positive divisors, positive prime divisors actually. Either P divides A or A and P are coprime, right? And you remember what that means. What did coprime mean? Coprime meant, this means what? This means GCD of A and P is 1, right? That's what we meant by coprime. Some people would also call it relatively prime. So that's point number 1. Point number 2, if P divides AB, then P divides A or P divides B. All right? Could be that it divides both, right? So here's the proof. First of all, notice that the GCD of AP is a divisor of both A and P, right? So what's that mean? That means, well, if you get a divisor of a prime, it's either 1 or P, right? If it's equal to P, then that means P is a divisor of A, right? There's one possibility. And if the GCD is 1, that means A and P are coprime. So there you go. That's the proof of part 1. It wasn't especially, it's almost a corollary to the definition, honestly. All right, next up here. This one was a little bit more intricate, the proof, I suppose. If P divides AB and P does not divide A, right, then what do we want? If we want to prove it, either P divides A or P divides B, right? And here A and B appear symmetrically, right? So suppose P does not divide A. Then we need to show what? P divides B. So let's see how that goes. So suppose P divides AB and P does not divide A. All right, then following the argument from 1, we find that the GCD of A and P is 1, right? Because either P divides A or A and P are coprime, so it must be in the A and P are coprime. So then by Bezout's theorem, we get U and V and Z, for which AU plus PV equals to 1, right? But then that multiplied by B times this gives me that. So I get BAU plus BPV equals to B. But that gives me that P divides what? Well, let's look at it. P divides AB by assumption, and P divides ABU. Well, that's just, if this is by assumption, well, excuse me, P divides AB means that P divides ABU. Okay, true. And P divides PBV, that's just obviously, right? If P is a factor, then P divides it. So what do you have? P divides this, P divides that, so P divides B. But that's what we're trying to show. So there you go. That is the proof of proposition 2, part 2. All right. Proposition 3 here. Proposition 3. So what we're looking at right now are just some basic results about how divisibility works with primes. Divisibility works really nice with primes. It's better than just, any old numbers. Primes are special. So if p is a prime and p divides a product a1 through ak, right, then that means p divides aj for some j. So if p is a prime and it divides some product of numbers, then there's got to be at least one number in there, somewhere in that list, that it has to divide. It has to fit in there somewhere. You can't straddle. You can't have half of the prime in a1 and half of the prime in a2 somehow. It doesn't work that way. All right? So here's how the proof goes. It's by induction on the number of things in the product. So first of all, if you have two things, then proposition 2, part 2, said that if p divides ab, then p divides a or p divides b. All right, so using a1 and a2 instead of a and b, there you go. So that's kind of the base case. Suppose inductively that p divides a1 through ak implies p divides a sub j for some j in 1 to k. All right, consider p divides suppose that p divides a1 through ak plus 1, right? Then we can just let the product of the a1 through ak be called a, and we can let the ak plus 1 be b, and again apply proposition 2, part 2, which tells us what either p divides a or p divides b, right? So p divides the product of a1 through ak, or p divides ak plus 1. So if p divides ak plus 1, then we're done, right? Because it divides one of the aj's in the list. But if p divides the a1 through ak, then by the induction hypothesis, we're also done because it gives us that p divides aj for some j in that list, right? So anyway you slice it, there's some j in the list of 1 to k plus 1, right? Because anything in 1 to k is still in 1 to k plus 1, fair enough, right? And so there you go. That's the induction hypothesis holds for k plus 1, and we conclude by mathematical induction that we're on the level here. So there you go. Up next here, proposition 4, as I've called it. Now, I think, I'm following Jones and Jones fairly closely here. So if you look at Jones and Jones elementary number theory, you'll find most of these results. I try to think through the proofs for myself, but if I like their proof, I just copy it pretty much, Okay, so if p is a prime, and p divides a to some power k, then p divides a, all right? And that means then that p to the k divides a to the k as well. So this goes back to one of our earlier results on divisibility. Because if we had a divides b and c divides d, then we had ac divides bd. So like if you put that into practice here, you get this implies that. If you repeatedly apply that earlier proposition we had on divisibility. Here it goes. So if p is prime and p divides a to the k, well, what is a to the k? It's just a times a times a times a times a times a k-fold times, right? So in other words, a sub j is equal to a for all j from 1 to k, and hence by proposition 3 we'd find that p divides a. Aha, but then p divides a implies p to the k divides a to the k by our earlier theorem on divisibility. All right, and if you're in doubt about like this implies that, I would encourage you to just work it out from the definition. It's something you should be able to do. Right, like literally from the definition of divisibility, you could get this implies that. Here, I'll do it on my, I don't want to do it on my cover sheet. Let me, I'm kind of low on blank white paper at the moment, annoyingly. Check this out though. P divides a implies a is equal to pj, right? Which implies that a to the k is equal to pj to the k, which by the way is p to the k, j to the k. So what does this show? This equation right here, it shows that a to the k is a multiple of p to the k. So that tells me that p to the power k divides a to the k. See? So if you're fuzzy on the theorem from the previous lecture, then don't let that get in your way. You can prove it directly from the definition, just like that. It doesn't have to be hard. So I need a secret word. Ah, the secret word is wizard. There we go. All right, next up. So now we're going to take a little bit of a detour from the study of primes for their own sake and look at an application of the concept of primes to the problem of irreducibility of polynomials with integer coefficients. Polynomials with integer coefficients is just what it sounds like. You got a polynomial, all of the coefficients are just numbers, right? Whole numbers or negative numbers or zero. And then the question is, when can you factor in that context, right? In other words, this is kind of the factoring we tend to focus on in like a remedial algebra course or something, right? Fractions in some sense aren't allowed. You're only allowed to do whole numbers. Well, that's this universe, right? So a polynomial with integer coefficients is reducible over z if there exist polynomials g of x and h of x that factor it like this, right? This is, I would call this a reduction of f into g of x times h of x. And if f of x cannot be reduced over z, then f of x is irreducible over z. Okay. Now, these problems are pretty formidable without the concept of prime, but with the concept of prime, it's interesting, but we can actually kind of find a way to carve through these kind of problems. And one of the fundamental tools that will give you some really nice examples with very little work is known as Eisensteins criteria. So here's Eisensteins criteria. If f of x is a polynomial with integer coefficients, a0, a1, an, and these coefficients are such that p divides the constant, the first one, all the way up to the next leading order terms. So p divides all of these, but p does not divide the leading coefficient, a sub n, all right? And p squared also does not divide a sub 0. Given all this setup, then f of x is irreducible over z. By the way, you know, if f of x is monic, as often it is, then a sub n is equal to 1, and p does not divide 1. So that's kind of, so this one condition here, that p does not divide a sub n, often we don't even think about that. I don't think about it anyway. I should think about it, but I often don't. I should think about it though. It's for free if you're working with a monic polynomial, you know. All right. So here's the proof, and let me make sure it's all visible here. Try to talk through it here. So what we do is we suppose that there's a reduction of f of x, all right? And we're assuming that f of x has coefficients a0 through an, which satisfy the conditions of Eisenstein's criteria, right? And then we're supposing we got g of x and h of x with coefficients using b's or c's, and the degree of g is s, the degree of h is assumed to be t. All right, and I'm assuming that the degrees are larger than or equal to 1, so that it's an interesting reduction. Then, if you multiply out, if you think about, well, think about things here. So first of all, f of 0 is g of 0, h of 0. In other words, how are the constant coefficients in the original polynomial and the reduction related? Well, a sub 0 is c sub 0, b sub 0. That's easy to see if you just think about multiplying out the g of x and h of x with this form and that form. Of course, c0 times b0 must give you a0, right? But we have p divides a0, so that means p divides c0, b0. And we're also assuming p squared does not divide c0, b0. So if you think about this, what this means is p has to either divide c naught, or b naught. It can't divide both. If p divides both of these, then p squared divides their product. All right, and that's assumed to not be true. So this means without loss of generality. See the way that b and c appear in this proof? There's really no distinction. Okay, so if we can make an argument assuming p divides b naught, then the argument which follows, we can just reverse the letters b and c and have the same logic. So there's no loss of generality here, assuming that p divides b naught. And p does not divide c naught, all right? So p does not divide bs. Let's see here. Why is that? Because if it did, then p would divide the leading coefficient. See, because the leading coefficients of the reduction give you the leading coefficient of the thing they're reducing. See, a sub n would be b sub s times c sub t, right? So, right. So we know that p does not divide b sub s, because otherwise it would contradict p not dividing a sub n. Hence, there must exist some I be less than s, such that p divides everything up to that point, but not I, right? Because it doesn't divide b sub I for the maximum choice of I, which is s. All right. So if we consider a sub I then, which is b0 ci, this is just how do you multiply polynomials. So ai is b0 ci plus b1 ci minus 1 plus dot 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 bi minus 1 c1 plus bi c0. Then we have p divides a sub I, and we also have p divides all of this. So, well, everything except for the last term here, right? But if you divide this and you divide all of that, then you divide the last term as well. So p divides bic0. But by proposition 2, part 2, we have p divides bi or p divides c0. If p divides c0, then as p divides b0, we have p squared divides b naught c naught, which is a contradiction. So p squared does not divide p naught c naught, of course, right? Likewise, if p divides bi, well, that's a problem because p does not divide bi by assumption here. So any way you slice it, we get a contradiction. Consequently, we have Eisenstein's criteria. If you meet this criteria, your f of x is irreducible. That is really nice because if you think about the problem of showing irreducibility for just arbitrary polynomials with integer coefficients, it's kind of scary. Like, how do you think about all possible factorizations of these things? And let me show you why that's like more scary than you might think, because it turns out that there are polynomials over the integers which cannot be factored of arbitrarily high degree. This one, for example, x to the n plus 9x plus 3. So I have leading coefficient 1. The first, a1 coefficient's 9. A0 coefficient 3. I did this so that I get 3 divides a sub j for 0 and 1. And, well, you notice that when n is larger than 2, like if n was 4, you have a sub 3 is 0 and a sub 2 is also 0. So 3 divides 0. So all the 0 coefficients are automatically divided by 3. So we got 3 divides a sub j for j equals to 0, 1, 2. So this is 0, this is 1. Those are interesting, but everything else past 1, the coefficients are 0. So this is kind of, it's true, but it's also silly. So anyway, we got 3 divides all of the coefficients up to leading order, but not including. And of course, 3 squared does not divide 3, and 3 does not divide 1 because this is monic, as I was talking about. Therefore, by the Eisenstein criteria, f of x is irreducible over z. What's the degree of this f of x? It's n. So this means that you can find polynomials of arbitrarily high degree which cannot be factored over the integers. So another important example for us, because of the connection that the cyclotomic polynomials have with what are called roots of unity, I'll include here. So phi p of x is 1 plus x squared plus x to the p minus 1. It turns out that this is irreducible over z. Let's see why. So what we do is a little trick. We let f of x equal to phi of p of x plus 1. Notice that if I can reduce this f of x, then that gives me a corresponding reduction in phi p, because phi p is f of x minus 1. So if I could reduce the f of x, then it would likewise reduce the phi p of x. So I get everything I need to see from studying f of x rather than phi p of x directly. So what I'm going to do is I'm going to look at, I'm going to try to get information about f of x, which is phi p of x plus 1. All right. So it starts out with like a little bit of a trick here. X to the p minus 1 factors as x minus 1 times x to the p minus 1 plus da 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 plus x squared plus x plus 1. But this is exactly phi p of x. So we have this kind of cute little formula that the pth cyclotomic polynomial is, one way we could write it is as x to the p minus 1 divided by x minus 1. All right. Think of this as a mnemonic for canceling that out. Right. Now, but on the other hand, we have f of x is phi p of x plus 1, right? So if I plug x plus 1 into this formula, I get x plus 1 to the p minus 1 divided by x plus 1 minus 1, which simplifies to 1 over x times all this lovely stuff, right? So here I'm doing the binomial theorem on x plus 1 to the p to get all these terms. The 1's cancel, and you're just left with x to the p minus 1 plus all these terms, right? But notice that explicitly, p, of course, does not divide the leading coefficient as 1, but all of the binomial coefficients have a p in them, right? P choose 1, p choose 2, p choose p minus 2, p choose p minus 1. So p divides all of the next to leading coefficients, right? And the constant one, the a sub 0, if you will, it is equal to p. And of course, p is not divisible by p squared. So by Eisensteins criteria with prime p, we find that the pth cyclotomic polynomial is irreducible over z. So like, you know, well, anyway, that gives us a lot of, we'll come back to that later in the course, most likely. It's an interesting application of Eisenstein's criteria here right now, and I'll try to, give you some homework problems where you get to try out your hand at Eisenstein's criteria for some examples. Listen, there's another way to check irreducibility or reducibility of polynomials with integer coefficients that we'll study in a few lectures from now, so we're not quite there yet, but this is the first of like 2 tools we have pretty much to study this problem. But finally to the main event, the fundamental theorem of arithmetic. All right, so here it is. What is the fundamental theorem of arithmetic? It is that each positive integer n has a prime power factorization in terms of what? In terms of distinct primes p1 through pk and powers e1 through ek, all right, all larger than or equal to 1. And this is unique up to the order of the factors. So I'll start with the existence part of the proof, which is actually by, let's see, what was it by? I'm trying to remember. Well, it's by strong induction. So here we go. So to prove existence, begin by noticing that if we look at 2, right, that's the first thing. If the proof is by induction on n equals to 2 is the first n, which meets the criteria of the theorem here. So 2 is 2 to the 1, so that fits this pattern. Great. So next, we'll suppose that all the way from 2 to n minus 1 all have prime power factorizations. Consider n then. That's the next one, right? So if n is a prime, we're done. Otherwise, n is composite, which means that there's some a and b between 1 and n. And so by the induction hypothesis, we can find prime power factorization of a and a prime power factorization of b. And so multiply them, then you've got a prime power factorization of n. Of course, we have to collect, if there are any prime powers which coincide, you have to put them together. And so making that adjustment will then have a product of the distinct prime powers, right? And so therefore, by induction on n, we find all n greater than 2 have a prime power factorization. So that leaves the problem of uniqueness. I think my proof of uniqueness here is so-so. I mean, I've got part of the proof written out here, but you could improve it, I'm sure. But I'll just kind of talk us through here what I have. suppose you have two different prime power factorizations of a given n, right? I'm using p's through pk's and q's through l's for the other one, right? Where p1 through pk and q1 through ql are distinct lists of primes. Notice that p1 divides n, right? So that means that p1 has to divide one of these q's. But qj is prime, right? And p is not equal to 1, which means that p1 is equal to qj for some choice of j. So if we take n and we divide by p1, we would also have, p1 to the e1 minus 1, and the power of the jth q prime gets reduced by 1 as well. But we can repeat this process, right? And we can basically divide out by the power of p1 to the e1. And so remove p1 from the list of primes on the left-hand side. And on the right-hand side, we'd have fj raised to the, that's supposed to be qj, my bad. Qj raised to the fj minus ej power, right? But as fj is equal to p1, we find that p1 divides this guy, right? So that means p1 divides pj for some j in 2 to k. Sorry, I suppose technically speaking I should use j as a variable here, or I don't know, I need to do something to make it a little bit different. I'm going to introduce a new notation. Check it out. J dot dot. There you go. J dot dot. J double dot. Sorry, it's stupid. Anyway, so for some j double dot in 2 to k, that's impossible, but because p1 is not equal to pj, for p1 is not equal to j double dot, for j double dot not equal to 1. So therefore, it must be that fj is equal to ej, because otherwise you get an unwanted copy of p1 over here. And then basically you just continue in this fashion until you cancel out everything. And then the thing I haven't written out, of course, is that at some point, if you ran out of p's and you're just left with q's, like if k wasn't equal to l, then you'd have excess primes on this side equal to 1, which is absurd. So you have to have the k is equal to l by the continuation, the ultimate endpoint of this process. Now, so that's essentially the proof. All right, and this is the fundamental theorem of arithmetic, because there are a lot of questions of arithmetic which you can settle by knowing these fact that every integer has a prime power factorization. So like, here's some ways to look at some of the calculations we've done before in terms of primes now, which I think I'm not telling you anything that you didn't learn as like a child, right? But, maybe not with this kind of intense notation that we're using at the moment, but still, it's really not new to you, I don't think. So, if we have numbers, a and b, then we can say make a list of p1 through pk to be a list of the distinct prime factors in both a and b taken a and b together. So, and here we're allowing the power to be 0. In other words, like, here's my example. So 31,500, right, is A. 13,475 is B. So 5 cubed, 6 squared times 7. 5 squared times 7 squared times 11. So like there's, well, it's better to look at it this way. 2 squared, 3 squared, 5 cubed, 7. 5 squared, 7 squared, 11. So this one is missing the 11. And that one is missing the 3. So, but we can write, if we take the list of distinct primes collectively, we've got 2, 3, 5, 7, and 11 for this a and b. And so by making sum of the powers 0, we can always write a and b as a product of the primes of both of them. It's just we use some 0 powers. That way we can use the same list of primes for both numbers, which is nice because you saw the kind of hassle it was to use like p's for the one number and q's for the other one on the previous page, right? So this is kind of nicer. But anyway, when you multiply the numbers, you just add the exponents of each prime factor. When you divide the numbers, you subtract the exponents of each of the prime factors. If you take the nth power of a number, you just take the nth power of each prime factor. And the GCD, you just take the minimum of each prime factor, which appears. So, you know, if there's 0 for either one, then it doesn't get included, you know. And the least common multiple, on the other hand, you take the max of the exponents for each prime factor. So I think this, I mean, okay, maybe this makes sense. I think it'll make more sense if we just look at the example. Like, so the GCD of AB, so since there's no 2 in B, essentially, we don't put a 2 in the GCD, right? Since there's no 3 in the B, we don't put a 3 in the GCD of AB here. But there is a 5 squared, which is in both of them, right? Because 2 is the minimum of 3 and 2. So we get a 5 squared in the GCD. And there is a 7 common to both of these because the minimum of 1 and 2 is 1. So we get a 7 to the 1. And since there's no 11 in A, we don't put an A in there. But we do get 7 times 5 squared, which is 175. And it turns out if you calculate the LCM of what's left over, you know, the max, 2 to the 2, 3 to the 2, 5 cubed, 7 squared, 11 squared, you get this number, what, 2,425,500. And it's pretty neat. If you multiply A times B, you get this big old number here. And if you take that big old number and divide by 175, you get the 2,425,500 again, which is what we proved without the help of primes before, right? We proved these things using other ideas, which are related but a little bit different. But now that we have this world of, you know, prime calculations, you can go back and revisit this theorem and you can prove it using the prime power factorization. I think the proof is pretty easy in this way of doing things. If we multiply the GCD times the LCM, then that's P1 minimum plus maximum of the, so like I get the minimum from the GCD, I get the maximum from the LCM, and that happens for each one of the primes. But if you think about min plus max of EJ, FJ, you just get EJ plus FJ, right? Because either one of these or the other of them is EJ and vice versa for FJ. So however you slice it, it has to be EJ plus FJ. And that gives you back AB. Kind of nice. One last thing. If P is a prime and P to the E plus 1 does not divide N, but P to the E does divide N. Alright, sorry, my green marker got a little bit wonky there. Then we write P to the E divides. I think this is read exactly divides N. Alright, so basically if P to the E exactly divides N, that means that P to the E is the prime factor, prime power factor, which appears in N, right? So like 1250 is 10 times 125, which is 5 times 2 times 5 cubed. Excuse me, goodness gracious. Which is 2 times 5 to the 4th. So 2 divides 1250, and 5 to the 4th divides 1250. I mean, exactly divides, right? And so like, my example 7 is really more of a theorem than it is an example, truth be told, but if you have distinct primes, P1 through PS, and their power is E1 through ES, and N is equal to that prime power factorization, that's true if and only if P to the E to the J, P sub J to the E sub J, rather, exactly divides N for each of the alleged prime powers 1 through S, right? And one last theorem here. If you have A1 through AS mutually coprime positive integers, and suppose that the product of them collectively is the nth power of some x, then there exists x1 through xs for which xj to the m is equal to a sub j for all j equals 1 to s. In other words, if a product of mutually coprime integers is equal to a mth power, then each one of the coprime integers appearing in that product is itself an mth power. All right? And the proof is basically just using the prime power factorizations of these things and sorting through what coprime gives us. So since the GCD of AI and AJ is 1, that's what it means to be mutually coprime, right? So there are no prime factors, common prime factors shared between A1 through AR, right? Which means, here's my horrible notation for this problem, you can make a distinct list of primes for the totality of all these things, P11 out to P1I1 and all the way out to PS1 and PSIS. So here's my distinct list of primes for this list of S numbers. And so here, I mean, A1 is that, A2 is that, AS is that. So if I take x to the m, I have it's equal to all of this, right? And that's supposedly equal to, this is my prime factorization of x itself, right? Q1 to the F1, Q2 to the F2 to the QT to the FT to the M, which by algebra is Q1 to the F1 to the M, Q2 to the F2 to the M, and so forth. But then by uniqueness of prime power factorizations, it must be that QK to the FK to the M has to be equal to like P11 to the E11 for, you know, for some choice of K. This guy has to match, you know, that one. There has to be some K in here which matches the first one, right? And so that tells me then that P11 is equal to QK and E11 is equal to MFK. But, you know, I can repeat this argument and get it for every prime power. So every prime power over here has to be a multiple of m, all right? And so since that's the case, then we can factor the m out to the outside and we get the product of pj1, k1, da, 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 pjij, kij, all to the m power, which is what the claim was. So my apologies for this proof. I love indices and notation. Like, you can read Jones and Jones. They have an argument which has no notation. It's just a paragraph, and if that makes sense to you, well, more power to you. So anyway, that's it for Lecture 7. Next time we're going to be talking about structure of primes. So there we get to learn a little bit about some of the more famous theorems of number theory. So thanks, guys.